Tickets. You should bring your tickets. This is a little race. Alpha Fall. Meet the bus outside. Thank you. Our last speaker of the group is Dr. James Cusimano, and we've invited him particularly to address the subject of molecular engineering and catalytic materials. Tim?
Well, thank you, Alice, and thank you, ladies and gentlemen. It's a pleasure to be here. This is actually the second time that I've had the opportunity and privilege to address this distinguished symposium. The first time was almost 20 years ago when I presented my thesis research at this same symposium in Atlantic City. And that was a rather detailed technical presentation. The presentation that I'm going to give you today, although it will have some chemistry and chemical engineering, will indeed be more of a philosophical presentation. I guess that's the license that one is allowed after 20 years. Hopefully some wisdom will come forth with that. Now, my objective is to do something that I believe this symposium is doing, but perhaps in a more focused way, and that is to remind you of the tremendous progress that we have made in catalysis research and development over the past several years. And indeed, I believe we have entered the era of molecular engineering, of catalytic materials, and process technology. Now, I want to make two things clear. I'd like to go to two comments that my good friend Jim Roth made. Indeed, I am not talking about a priori catalyst design where one can sit down at a computer and design a catalyst, although I believe in our lifetime we will move substantially towards that direction, or towards that goal. Second of all, Jim made a very interesting point at the end of his presentation, and I concur with it wholeheartedly, and that is, if we are to get on a new growth curve and to create new technology, we need to look for discontinuities. And I would propose to you that the methodology of molecular engineering in concert with good chemical engineering and an eye to the marketplace will make that happen. Now I'm going to focus primarily on industrial catalysis, although to be sure much of what I say will have general applicability. I asked myself, what is the most critical thing that one has to have in order to be able to do molecular engineering? And I came up with a one-word answer, and that is commitment. One needs to develop people and environment. You need to have lots of equipment. Some of it's quite expensive. You need to draw on data from a multiplicity of various areas of research, and to be able to use that in a very clever way. And I wanted to find a way to relate to you my idea about commitment. So if I can have the first slide. And bring the lights down, please. This is a story of a chicken and a pig who are walking down a rural road, and they come across this billboard, which, as you can see, says, "Have a solid breakfast." And the chicken says to the pig, "Isn't it wonderful how we are feeding humanity? My colleagues and I are laying eggs by the dozens every day. Look at those luscious eggs up on the plate, those two crisp pieces of bacon. I really feel committed to feeding humanity." And the pig looked up at that billboard and looked the chicken in the eye, and he says, "Let me tell you about commitment." That's a message especially for all of you who are involved in research management. It takes time, it takes commitment, and it's not something that you can turn on and off. Now, what I'm going to do is very quickly talk about the opportunity for developing advanced catalytic technology by the methodology of molecular engineering. I'm going to say something very briefly about economic incentives. Some words have been said previously by a couple of the speakers. I'll tell you what I mean by molecular engineering. We'll give some examples and then look to future directions. Indeed, when you think about the opportunity, it simply flows from the technology requirements today. with respect to the chemical industry, and I think you're well aware of it, but let me just remind you. We need to develop process technology which uses low-cost raw materials. We need to have simple process design for low capital investment, ease of operation, and I assure you, not only economy on large scale, but economy on small scale. And we don't have time to go into this, but economy on small scale and capital investment are very closely related. Third, minimal energy requirements. I think, as Alex pointed out, sure, the oil embargo came about and the price of oil has gone down, but I can assure you, in my view, in the 1990s, we will see a resurgence, and I think we're seeing it move in that direction already with increased oil prices. And finally, this needs no explanation. The world indeed has changed in this area. Environmental compatibility and safety go without question. Catalysis addresses every one of those issues. Now, the economics, the number of $750 billion of materials, primary materials seeing a catalytic step, greater than 25% of our gross national product. That number comes from Catalytica and was developed about 4 years ago in a study that we did. I'd like to point out another one, which was recently announced by Intel, where they point out that innovative catalysis in molecular engineering could save more than $100 billion in the United States alone over the next 15 years. Now, what is this thing we call molecular engineering? Very simple. We start with a hypothesis, we synthesize materials, we characterize them, we test them, we post-characterize, and we modify and go around in this loop until we have a product or a process. Well, that looks pretty much like what we've been doing in catalysis research for the past few decades, and indeed it is. The big difference is the size of these boxes have changed. We now have a whole host of materials that we can draw upon from material science, from inorganic chemistry, organic chemistry. And I don't have to convince this audience that there is a whole arsenal of equipment by which we can characterize materials above and beyond what we could